Pacifica Radio presents an interview with Robert Moog, designer and builder of the Moog Synthesizer. The interview and demonstration of the synthesizer was conducted in the studios of R.A. Moog Incorporated at Trumansburg, New York. This is Gene Endres for Pacifica Radio, and today we're in the studio of Robert Moog at R.A. Moog Incorporated in Trumansburg, New York. Now, many people out there may have heard of Mr. Moog and his synthesizer, commonly known as the Moog Synthesizer. And today we came up here to Trumansburg to see if we could talk to Bob Moog about this, get some demonstrations of what the synthesizer is like and what it can do, and possibly even talk about some other aspects of electronic music today. Good morning, Bob.
Hi, Gene.
I was wondering if we could sort of start with the synthesizer itself.
But let's begin with a few concepts, a few ideas about the synthesizer. First, so our listeners can visualize it, I'll describe in somewhat more detail than you have what the instrument looks like. At the base of the instrument, there are a couple of keyboards. At least the one we have here has two keyboards. They're conventional organ keyboards. However, they're not used in a conventional way. Behind the keyboards and above is a large cabinet full of panels. There are many small panels. Each panel is actually a separate instrument. Each instrument is part of the synthesizer and is used to do one thing toward either generating or modifying or shaping in some way the resultant tone. To use the synthesizer, the musician connects together these components, just as an instrument builder would put together the strings and the fingerboard and the body of a violin in order to come up with a complete instrument. The parts of the synthesizer each have musical meaning, so it's not necessary at all for the musician to think in electronic terms. He has to understand what a signal is. A signal is a variation of electricity that carries some information. He has to understand what an input is and what an output is. But then most people these days understand that. In fact, if you've hooked up your hi-fi set, you automatically know all these things. So there are two things involved in setting the synthesizer up. One is the interconnecting of the various parts of the synthesizer with patch cords. The second is the setting of the operating points of each of the individual instruments by these control knobs. For instance, we begin the production of a pitched tone in a device called an oscillator. Technically speaking, an oscillator produces a waveform that repeats regularly. Musically speaking, an oscillator produces a tone with definite pitch.
Could we have a demonstration of an oscillator?
Here is a steady oscillator tone. Remember now, we haven't begun to shape it at all, and that's why it sounds fairly mechanical and monotonous. But by changing the dials, I can move the pitch up and down. And by selecting the appropriate output from the oscillator, I can change the waveform or the tone color. The first waveform we played was a sawtooth waveform, and if that were displayed on an oscilloscope, we'd see that the waveform consists of a straight line that rises gradually, and then another straight line that falls abruptly, just like the teeth of a saw. Let's hear the sawtooth again. When we describe an electrical signal in terms of its waveform, what we're describing is how the signal varies with time. And what the oscilloscope presentation is, in fact what the waveform itself is a graph, a plotting of the electrical force versus time. Our ear, as it turns out, doesn't hear time variations explicitly. Our ear hears another parameter or variable, and that's frequency. Our ear hears that as pitch when there's one frequency, and when they're all together, our ear puts these together, processes them, and comes up with a pitch of a given tone color. We can describe a given waveform in terms of its spectrum or frequency content, just as we can describe it in terms of its time variation or waveform itself. A musician would say that the sawtooth waveform has all of the overtones that a periodic or pitched waveform can have. Other waveforms have less harmonic content or different distributions in its spectrum. For instance, the sine waveform here has almost no harmonic content.
That gives a kind of flat, nondescript sound.
Yeah.
Right.
Some of your listeners may be familiar with the activities of the earlier electronic music composers who used sine waves a great deal because it happened that sine wave generators were readily available from laboratory instrumentation. In the total spectrum of waveforms that can be generated, the sine wave is the dullest sound. It only has one frequency component, and it's an extreme which an electronic musician would use to compare all other tone colors or waveforms, just as the lowest note on the piano is the extreme pitch of a piano, which is played very seldom but serves as the bottom or the reference for all the other notes.
Bob, there isn't any musical instrument that produces a sine wave or nearly pure sine wave by itself, is there?
No, the closest we come is the very high parts of the flute or clarinet register, or perhaps the oboe register, but just the very highest notes. The lowest notes of all the woodwinds, as well as all the brasses and the string instruments, produce very rich and complex waveforms. Waveforms that not only have a great many components or overtones in their spectrum, but also these components vary constantly with respect to one another, giving the tone a life and a richness that we call musically pleasant.
Okay, so now we've sort of taken two tones so far, the sawtooth and the sine wave, and there are two more available in the basic oscillator of the Moog, right?
Yeah. Another one very much like the sine is called the triangular. Its waveform is composed, just for the record, of two straight parts that rise gradually and fall gradually. There's no sudden, abrupt change in the waveform. And here it is. The overtone content of the triangular wave is mostly odd. That is, the overtones are given numbers. We'll call them the partials, numbers of the partials. We have the first, the fifth, the third, seventh, and so on.
In other words, these would be frequencies that are multiples of how many times the original frequency.
Right.
If you considered a sine wave as a frequency of 300 cycles, in a triangular wave you'd have overtones which are multiples of that.
That's exactly right. We don't hear these pitches explicitly. We hear them rather as a contribution to the tone color. I do have a device connected in now to the signal path, a device called a filter, which we'll get back to later, but I can use it now to emphasize these harmonics one by one, and when they're emphasized in the way that I'll do in just a minute here, you can hear each harmonic, each overtone explicitly. Let's go to our back to our sawtooth that has all of the overtones. Now I'll bring the filter in. Now I'll change the setting on the filter so that each of the overtones is emphasized in turn.
And that basic note that we ended up with is very like a sine wave.
That's right. That's exactly right. In describing the spectrum, we say that each of the frequency components, which are whole number multiples of the fundamental pitch, was emphasized in turn. In the time domain, and that is in describing the waveform, we start off with something that's basically a sine wave, then looks sort of like a sine wave twice as fast, and then a sine wave 3 times as fast, and then a sine wave 4 times as fast, and so on.
One thing I'd like to emphasize, Bob, it isn't truly necessary for, let's say, the musician to totally understand, let's say, the mathematics or electronics of what is going on here. He can use his ears to judge what is happening, right?
Yes, a few electronic musicians do have a detailed mathematical knowledge of acoustics and electronics. However, most of the musicians that we've worked with use only their musical intuition as well as basic rational processes to determine what's going on and how to work with the material.
Yeah, I wanted to emphasize that because this is almost the central thing of the Moog synthesizer, that you don't necessarily have to be an electronics genius or a mathematical genius to make music with it.
Right.
Okay, could we go on finally to the last kind of oscillator?
Yeah, all these tones come out of one oscillator. They're just different outputs.
I see.
The last one is called a square wave. Actually, the general name of the waveform is going to be called rectangular, and what I'm going to play now is a square wave. A rectangular wave is a waveform that rises abruptly, proceeds at a level value, then falls abruptly, so it looks like a bunch of rectangles. When the up portion is the same width as the down portion, then it's called a square wave. And here's what a square wave sounds like. A square wave, like the triangular, has only odd harmonics. However, the harmonic content is much greater, and that's why the note sounds more brighter and more bright and raspy. Let's compare once again the square wave with the triangular. That's the square. That's the triangular. Now, as I change the width of one part of the rectangular waveform with respect to the other, this waveform change drastically changes the makeup of the spectrum. Even-numbered overtones are introduced and some of the odd ones drop out. I can change the overtone distribution continuously by turning just one knob here.
All right, those are the basic oscillator sounds of the synthesizer. Now, as I understand it, there are a couple of other kinds of sounds that it can make. I was referring to the noise generator.
Yeah. Before we get to the noise generator, I'd like to point out how these oscillators, which basically produce pure pitches, can be also used to generate noise sounds that approach noise equality. These oscillators can be controlled, that is, their pitches can be changed by the application of any varying voltage that's available anywhere else in the system. For instance, if we use a voltage from another oscillator, this is a periodically varying voltage, we can actually periodically vary the pitch of what we're listening to. Let's try that. We'll, as a varying voltage, as the control voltage, we'll use another sine wave, which is going very slowly.
Okay, now the basic tone is the tone of your oscillator, which is...
It's the same square wave that we listened to before.
But there is another wave that is going up and down at that slower rate that's causing your first wave to vary
exactly.
that way.
Well, there are two oscillators involved here. One is what we're listening to. That's what we hear. This is called the audio oscillator. The second is making the voltage that's changing the pitch of what we're listening to. That's called the control oscillator. In terms of actual hardware, these oscillators are identical. It's how they're used that determines whether they're audio or control. Now let's speed up the control oscillator. We'll hear what happens as we do that. There, now the control oscillator is going fairly rapidly, about 20 or 30 times a second. The variations in the audio oscillator that are produced by the control oscillator are going too fast for our ears to follow it explicitly. So what our ear hears is sort of a texture rather than an explicit up and down contour. The faster the control oscillator goes, the finer this texture comes, and after a while the resultant tone has additional frequency components in it, additional overtones which are not whole number multiples of the fundamental frequency, which for the techie types are called sidebands, and which give the resultant tone a clangorous or quasi-pitched sound, a sound partway between a pure pitch and a pure noise. So let me go up again from where we left off. Now, as I slid up gradually, you could hear these sidebands going up and down while other components stood still, and they crossed one another. It's very reminiscent of the whistles you get when you tune in an AM radio sometimes, and actually it's very much the same phenomenon.
By the way, Bob, I wanted to mention that you used not a keyboard on varying that particular note, but another kind of controller.
Right. We have a total of 5 controllers here on this particular synthesizer. 2 keyboards, 1 ribbon controller, which is just a flat metallic ribbon stretched out, about 2.5 feet long, and 2 pedals. All 5 do basically the same thing. They produce a control voltage which can be moved up and down by the motions of your hands or feet. The keyboard allows the musician to make discrete changes in a control voltage rapidly. That is to actually play notes.
Stepwise.
Yeah. Like so. The ribbon controller allows us to slide the pitch continuously. And the pedals also allow us to slide, but in a much grosser and less controlled way. The pedals are used for the less sensitive parts of the sound, like the loudness or the tone color. Any of these can be used in combination with any of the others. And we have a resident composer, Chris Swanson, now living in Trumansburg, who has developed an extremely subtle technique of using the ribbon controller in combination with a keyboard to produce pitch inflections in the jazz-oriented material that he writes, inflections that are extremely expressive and most people would not believe would come from a keyboard if they didn't see it.
Okay, now we have our basic tones here. Let's see what you can do with them. This is just a very small part of the capability of the synthesizer right now, and there's a lot more that you can do to it, or with it.
Why don't we show what white noise is like
Okay,
now?
there are other kinds of noises, not regular oscillations, that can be produced by the synthesizer.
Yeah. Now here we use the term noise in an objective technical sense to mean a completely random signal, a waveform in which the height at one part is absolutely uncorrelated with the height at any other part. What this means to the musician is that the sound has absolutely no sense of pitch, that the sound energy is distributed uniformly throughout the audio spectrum and has low components as well as high components. That's white noise. It's the very same noise that you hear over your FM set in between stations. Just for the record, we have another type of noise called pink noise, which has more low frequency content than high frequency content. And it's called pink noise in analogy to pink light, which has more of the low frequencies, the long wavelengths of light than the short wavelengths. Here's pink noise.
Could you switch back and forth between white and pink?
Yes, I can. White, pink. About a third of the synthesizer is devoted to generators, instruments that produce periodic waveforms, that is oscillators, or that produce random waveforms, like the white noise here. The rest of the synthesizer is devoted to shaping these sounds, either shaping their spectrums, shaping their amplitudes or sizes, or producing the control voltages that actually do the shaping.
Could we mention a minute just why this is so important to music and why the synthesizer is something special in terms of music, how the affecting certain basic noises can give you a whole range of sounds that may equal other known sounds of known instruments, or even in fact generate sounds that have possibly never been heard before.
People will look at all this stuff and they'll see an organ keyboard, and that will suggest an electronic organ, and they'll say, how is this different from an organ? Very common question. The answer strikes right at the heart of the value of the synthesizer. An electronic organ and a synthesizer are basically poles apart, whereas an organ has a very simple generator and shaper at each key, and a different one at each key, so that you can press one key and get one note, press another key and get the second note occurring simultaneously with the first. These notes you get from an organ have no variation from the beginning to the end. They start, they're at the same loudness as a rule, from the very beginning to the very end. The tone color doesn't change, the pitch doesn't change except for mechanical vibrato. The synthesizer only produces one or possibly two or three independent notes at a time for all this stuff, but most of its instrumentation, most of its components, is used to impart contours, time-varying contours, inflections, shapings, call them what you want, into the sound. And it turns out that in the most general sense, it is these variations that give musical interest to the sounds that we hear. Just about every instrument, every traditional instrument that exists, is characterized not by how the sound remains constant from beginning to end, but how it varies. For instance, the basic difference between a violin tone and, say, a trumpet tone is in the way it starts and the way the pitch changes as the note progresses. There's a very interesting experiment that anyone with a tape recorder can perform. Record a violin tone and a trumpet tone of the same pitch, then cut off the first tenth of a second of each of the notes, and try to tell which is which. It's very much harder. So our ear grabs on to these changes in the sound. It's what interests our ear, and as soon as the sound stops changing, our ear becomes bored. From the objective technical point of view, there is no longer information in the sound except a timing information of when the note's going to stop. But as long as the sound is changing, as long as there is motion in it, it's musically interesting, and our ear latches onto it, and is absorbed by it. Now, before we go and explore some of these changes, perhaps I can comment on the value of being able to precisely, continuously control these contours is to a musician. So far, what the public has heard of the synthesizer has by and large been the performance of traditional-oriented music with new tone colors and new sorts of inflections which, although they're distinctly electronic and innovative, they're directly related to the traditional view of music, the traditional method of constructing music. Historically, music has been made with instruments into which the performer has to pour his own energy. He can't do this for any length of time without either taking another breath or reversing the direction of his bow. So that musical gestures, once again historically, are the production of short tones and the assembling of these tones, tone by tone, into complete musical composition. It's an architectural way of constructing an aesthetic entity, where instead of overall shapes made of a solid block, we think of assembling the shape from individual bricks, individual pieces, brick by brick. On the other hand, it's always been possible for sculptors to start with a solid block of material and to shape that block with as large a contour as he's wanted to, without paying too much attention to how the block mechanically was assembled in the first place. This sculptural approach can now be applied at the mechanical level to music too. That is, a synthesizer like this can be set up to produce a tone having nothing to do with the actual physical energy that the musician is pouring into the instrument. And the musician can then use all of his energy, all of his intellect to introduce contours in the sound. The most significant, in my opinion, the most exciting electronic music is music that is sculptural rather than architectural in concept, where long contours which vary slowly, precisely, and with some complexity are used in place of the traditional notes of music as we've known it up till now. Okay, the first concept to explore here is that of amplitude or loudness variation. The amplitude contour of a traditional musical tone is called the envelope. So what we've done is called all contours that don't repeat, that go through a unique shape from the beginning to the end of a given sound, an envelope, whether they apply to the amplitude or the amount of harmonic content or even to the pitch itself. Let's listen right now to an envelope that we can impart to the amplitude of the sound. Here is a fairly long attack, and here's a very short attack. The longest attack we can generate here is 10 seconds. This envelope then immediately begins to fall with a second characteristic time. Here we have a 1 second attack time now, and a 2 second initial fall time, and it will fall to about a quarter of its original loudness. The third time is the final fall time after I release the key or whatever other device I select to trigger the onset of the sound. I'll set the final fall time now for a half second. This will be the same sound we heard before. With a half second fall time. As it turns out, the exact shape of this contour determines to a very large extent the tone color that we perceive. For instance, with a very rapid rise time of about 2/1000ths of a second and a fall time of about 1/4 of a second, we get a plucked string-like sound. Whereas with a slower rise time of about a half second and a sustaining level that doesn't allow the tone to drop at all, we have a more horn-like quality. The shortest envelope we can impart can be made so short that we don't even hear a sense of pitch. That is, the envelope doesn't include enough cycles of the periodic waveform for our ear to figure out what pitch it is.
Sounds like a pitched click.
Yeah, that's exactly what it is. The envelope is so short that our ear perceives it just as a click. This is one possible amplitude variation. We can superimpose upon an envelope a periodic contour. Let's do that.
By the way, sometimes you'll hear these clicking noises, which are actually placing patch cords that connect together the various parts of the synthesizer.
Here is a periodic variation of the loudness at about, I'd say 8 or 10 times a second, superimposed upon a decaying envelope. We can also use something like the pink noise to impart a random variation to the loudness. And this roughens up the sound quite a bit. We get sidebands from this process, which is called amplitude modulation, just as we get sidebands from the frequency modulation we heard earlier. And we can apply an envelope like this not only to the audio sound, which is what we heard, but also to a control voltage, which is changing the audio sound. Thus, whereas before we had a periodically varying pitch, now we can cause that periodic variation, which is caused by a control voltage, periodic control voltage, to build up and then die down in exactly the same way as the sound itself builds up and dies down. Do that again. This is a very gross and simple variation. It may or may not have any musical usefulness. It's up to the composer to use his discretion and his creativity to select just the right shaping, just the right proportions of all these things to come out with something that suits his purpose.
It's becoming apparent to me that a large part of composing with the synthesizer becomes just selection of the kind and variation of the sounds that you get, rather than taking a given sound and just manipulating it with notes.
Yeah, the most successful electronic musicians spend an awful lot of time selecting, throwing out, readjusting the controls to get just the right proportions of everything. when an electronic music composer begins, he's usually disturbed by the patch chords. It seems to him that connecting all these instruments together is a complicated and time-consuming process. However, that's not the biggest part of the problem at all. It's a mechanical problem which musicians very quickly overcome, usually within a week or two. Most of the time of a practicing musician is spent in adjusting the controls. And it's not unusual at all for a musician to spend several hours adjusting, listening, recording, listening again, and going back and working over the sound time and time again to get just the right shaping, just the right gesture for his purpose. All right, the next part of the sound that we can shape is the amount of harmonic content of the spectrum. The class of instruments that is used to shape the spectrum is called the filters. Okay, now we're going to explore a group of filters here. We call this a fixed filter bank. They're actually a collection of 14 individual filters, each of which allows through a portion of the frequency spectrum. Here's the note we're working with. And finally, the very highest part of the frequency spectrum. That's a very thin sound. It's a sound that has almost no pitch because of the highness of the partials that are being allowed through. Our ears are having trouble figuring out what the fundamental pitch is supposed to be from the relationship between these harmonics. But on all the others, our ear does indeed figure out the fundamental pitch, simply because the harmonics that are being allowed through are spaced one fundamental frequency apart. This filter bank is analogous to, in the visual world, to a prism that splits up the light into all its components, and then a series of shutters that allows through the different colors as they come out of the prism. And if we imagine a great big prism and a series of windows lined up in a row, one of which lets through the red light, one which allows through the yellow light, and so on, then we have a pretty good idea of the analog of what this filter does. This might be a little techie, I don't know. But
That's okay.
I'll tell you, it might be interesting to do the same operation to pink noise. So we can hear what the individual frequency bands of the pink noise sound like. Remember, the total pink noise sounds like so. Now let's allow through just the lowest portion. These are frequencies below about 100 cycles per second. 100 cycles per second is about an octave and a half below middle C on the piano. You can hear it's a very faint rumble like distant thunder. Now we'll go up in half octave steps from point about an octave below middle C on the piano. I'll just go up fast here. And finally the highest band. And once again, these can be combined. And so on. If you had enough fingers and could move fast enough, you could almost make a sculptural piece just by turning these knobs using pink noise as the source. Let's go on to another type of filter, a filter which, although much simpler than this fixed filter bank, can be voltage controlled and is actually more useful in imparting contours, time-varying contours, to the harmonic content of a sound. Since we just listened to an analysis of pink noise by this filter, why don't we return to pink noise as a source and apply it to what we call a voltage-controlled low-pass filter. Wow. Okay, here's our pink noise. The filter now is all the way open. That is, the cutoff frequency is at the top of the audio range. Now I'll turn the cutoff frequency down, and you'll hear first the highest components of pink noise being attenuated, then the highs and the middles, and then everything except the lows, and then finally you'll hear nothing. By changing a setting on this filter, we can cause the filter to emphasize a narrow band of frequencies right around the cutoff frequency. This will impart a sense of pitch, that pitch of the cutoff frequency, to the resultant sound. And what we'll hear is a whistle-like sound. I'll start once again at the top of the audio range using pink noise as a source, and we'll hear the resonance moving down in pitch. The importance of voltage control can be shown now. I'll use an envelope generator to sweep this filter open and closed. Here it is fairly slowly. Now let me speed it up some. Maybe cut down the amount of sweeping. Gestures like this produce new sound qualities. The sound that we've heard, like so many others we've just heard before, are characterized primarily by the variation from the beginning to the end. Here the variation was in the frequency at which the components of the white noise were emphasized.
Bob,
Yeah.
I want to talk about this more later, but let me inject this sort of briefly now, and maybe if you can
Okay.
answer it briefly.
Yeah.
I noticed from this kind of sound that we're generating a wholly new sound, and yet some of the sounds we had before, for instance, we compared to a violin or a trombone. Now, some people view the synthesizer as a device for making or imitating sounds of already known instruments, but you've shown that it can also be used to generate wholly new sounds. How do you view the attempts to use it just as an imitative instrument?
We're neutral. What we've tried to do here is build an instrument that's as general as possible, that doesn't enforce any particular aesthetic or any particular application upon the musician. People have accused us of slanting the instrument toward traditional musical applications in using the keyboard. We don't agree with that. The keyboard can be used to control any of the parameters, and once a musician begins to think in terms of the most general properties of sounds rather than playing notes in the traditional sense, then he's freed of the basic associations and limitations of the organ keyboard. I have to say that we're very grateful to the talented musicians who, by using the synthesizer capably to realize traditional music, particular, I'll say switched on Bach and well-tempered synthesizer, have demonstrated that all this mass of controls and patch chords is really a controllable, playable music instrument. I don't think there's much doubt that a work like Switched on Bach is a valid musical effort. I think that in the long run, the work that will turn out to be most significant is the work of people who approach the synthesizer as a completely new instrument, in fact, a completely new medium of musical expression. We've just gone through use of the low-pass filter and the fixed filter bank in filtering pink noise. There's one other filter I might demonstrate here. This is a high-pass filter. It does just the opposite of what the low-pass filter does. It filters out the lower frequencies and leaves the higher ones. And here's all the pink noise. And here's just the thinnest, highest portions. There's the top of the audio spectrum. Well, let's return to our pitch tones from the oscillators. Here's our old friend, the sawtooth wave. First, we'll pass it through the high-pass filter. Then through the low-pass filter without resonance. And with resonance. This is we did this before earlier in the program. Now, if we sweep the low-pass filter rapidly in its resonance mode like this, we get very vocal-like qualities. It's possible to set up the machine to pronounce just about any vowel possible. Setting it up to pronounce consonants is a bit harder because of the complexity of the voice and articulating consonants. The reason these vocal-like sounds can be so easily produced is that the voltage control filter in the resonance mode is a direct analog to what goes on in the vocal tract when we speak. The vocal tract consists of a generator, which is our vocal cords, which produces something very much like a rectangular waveform. And then it's a series of resonators, 3 of them, which we continually change the shape of, and in doing so change the resonant frequencies of. And they're analogous to these low-pass filters. What we hear primarily when we listen to speech is not the generator spectrum, but how the spectrum is being shaped by the filters. That is, our ear is able to extract all the information from the voice and process it in such a way that we know exactly how the resonances of uh, the vocal tract, the speech mechanism, are being varied. Now, let me say that as an engineer, I can tell you that if we were to build a machine to do this, it would be an awful lot bigger than an ear and a brain.
There have been people at work actually building machines that do synthesize speech and speech
Yes,
only, right?
yes. The telephone company and the computer manufacturers are interested in this for obvious reasons, all of which have to do with money. We're interested peripherally, since vocal gestures are possible musical material. In fact, they're obvious musical material, since a lot of music is singing.
Oh, one thing I wanted to mention before about ways to control the signal. Is it possible to control the sounds on a Moog with something like your own voice?
Yes, there is one modular instrument here, which I'm not going to demonstrate. It's not. I don't think we could explain it all clearly over the radio. It's called an envelope follower, and its function is to extract some basic information from external signals, external sounds. Information as to the way the loudness varies, what the average pitch is, and when the note stops and starts. In that way, the synthesizer operations can be controlled very crudely, to be sure, but it can be controlled by your voice or by any other external sound. There's one device here, which is not part of the synthesizer, but an accessory, which produces regularly repeating patterns, or don't even have to repeat regularly, they can be changed. This is called a sequential controller, and it has the same musical utility as a screen or a texturing surface would have in the graphic arts. And here's a note that is not changing as long as I hold one key. I'll use a sequential controller to impart changes in the pitch of the oscillator. When these changes occur less than, say, 4 or 5 a second, we hear them as discrete notes, because that's the way our hearing is oriented. But as I speed up the variations, just the variation itself, the speed of the variation becomes the important thing, and we have a texture rather than a note pattern. The sequential controller is controlling the pitch of the oscillator in exactly the same way as the keyboard does. That is, it's producing a control voltage which is applied directly to the oscillator. As it turns out, both the keyboard and the sequential controller are connected to the oscillator right now, so I can use the sequential controller to impart this texture, this patterning, and then move the whole pattern around, which itself is a pitch structure, with the keyboard.
this is where the idea that you were talking of before of the sculptural sound, the basic large block of sound that you generate to begin with comes
Right,
from.
right.
And then you start to work on that.
Yes, we think less and less in terms of notes and conventional scores, and more in terms of what graphic artists talk and sculptors talk in terms of texture, contour, overall form, tension, release of tension. These very general shapings that so far don't seem to be analyzable in the same way that the traditional music is by the music theoreticians. But they certainly exist, as is evidenced by the power of the music.
Bob, I was wondering if you could, let's say, take most of these parts that we've talked of now and build up a sound. You know, go through possibly one of the procedures that you might use if you're a composer working with the Moog, and just see how it builds up, how your ideas work as you're working with the different sounds and changing it. Could we do that?
Yes, let's first take a couple of traditional sounds. Sounds that, since we're all familiar with them, we know what they're supposed to sound like and we can talk about them. First I'll set up a horn-like sound, and then a plucked string-like sound, and then a timpani-like sound. This will be a very mechanical horn-like sound, but it will give you listeners an idea of how the musician thinks of when working with the synthesizer and shaping sounds. Here's one plain oscillator tone, unshaped. If we add a second oscillator at nearly the same pitch, we'll get a very slow beating, which itself adds a motion and a richness to the tone. A third oscillator an octave higher. This mixture now is fed through the filter. And finally, through the voltage control amplifier, which with the envelope generator will shape the loudness. The envelope generators are controlling both the loudness and the brightness through the filter. When I press the key, we'll hear the brightness and the loudness build up first slowly. I'll speed it up a bit. Of course, to accurately duplicate a horn tone, if that's what we want to do, we have to impart the pitch inflections that are characteristic of horn playing. No horn player in the world could possibly maintain a pitch 100% steadily the way these oscillators can, nor would he want to, because the pitch would, the tone color would suffer in comparison. And when we hear Chris Watson's music, we'll hear him imparting pitch inflections by using the ribbon controller. Pitch inflections which do indeed add to the interest and the appropriateness of these horn-like colors. To construct a plucked string-like sound, we begin with only one oscillator. Here it is, going at a fairly low pitch. Pass it through the filter and the amplifier, just as we did with the horn-like sound. But now the contours being generated by the envelope generators are reversed. Rather than building up gradually and staying high, we're going to start high and then decay to a lower value. Thus the note will begin loud and bright, and decay fairly rapidly to soft and muted. First, let's hear this variation slowly. I'll speed it up.
Again, these are attempts to make either a plucked string-like sound or a horn-like sound, but not an exact imitation of any known instrument.
Yeah, these are even worse than that. They're demonstrations of how you would go about it, not actually going about it. It's as if I were demonstrating how to bake a cake, and I throw everything into a pan and stick it in the oven, and throw out what came out of the oven. I mean, I'm not a musician, and I have almost no experience at constructing musically useful material. But the way I've gone about assembling the parts of the sound here is exactly the same way that the successful electronic musicians proceed when they work with the synthesizer. Now the next may come out sounding something like a timpani. We're using exactly the same setup, only instead of one oscillator, we're using two oscillators with a third, mixing them up by frequency modulation. Let's listen to the first one. And the second one. They're just separated by a little bit. Now together. And finally with the frequency modulation. So far it doesn't sound very much like a timpani. The shaping now is exactly the same as that which we've used for the plucked string sound. Here it is slowly. A little bit faster. These are fairly simple shapings, even when they're done right. They're applied to only 2 or 3 parameters or parts of the sound, and they don't last more than a second or two. And with a synthesizer of the size that we have here, it's possible for a composer to spend hours and days making the most detailed and complex shaping of a single sound imaginable. In fact, it doesn't even have to be a single sound. It can be an ensemble of sounds which are mixed and shaped as part of the same process. As an example of that, I'd like to play this sound sequence.